video help for problem 10.9. You can see a lot of numbers that'll help you do this from the written homework hints, but there's some things I'd like to say about, that'll complement it, I think. Part A, it's a two-dimensional imaging, which means that we will step in the gradient in the y direction, and for every value of the gradient in the y direction, it's giving us a vertical position, we will run it horizontally. We'll run for a time tr. That's a two-dimensional coverage of two-dimensional k-space. In B, this is chemical shift, and I kind of wish I had said a couple of these things for problem 10.8. You actually think about getting data for every point, nx times ny points in the two-dimensional k-space, kx, ky space. For every one of those points, you're going to then later run and take data over a time tr with no gradient, because you actually have kind of a gradient. You've got that chemical shift, you've got that fractional change in the overall magnetic field due to the chemical shift, the environment, the proton sees in different tissue, different molecules. And so the sigma B0, this is kind of like an effective gradient in sigma. And so that, I just wanted to kind of make that remark, and I wish I had said it before, pertaining to 10.8, as I said. Now in C, we do three-dimensional. That is, we've imagined, stepping in the y gradient and the z gradient so that we have ny times nz points, and for every one of those points, we run it horizontally along the x, gradient direction, the kx values, and so it's sort of like a bundle of needles in three dimensions. And each time we run it in the x, it takes time tr. In D, well, now we imagine we've got a box full of points in three dimensions, like we had a two-dimensional bunch of points in part B. So now I've got nx times ny times nz points covering all of three-dimensional k-space, and for every one of those points, it's the chemical shift, 4 dimensions. We run this thing later with no gradient on, just like in part B, and for a time tr. Finally, in part E, I just like to make the cultural remark that for field of view, sort of the image, the image size that we're looking at, we define essentially, when we look at something on our computer screen or whatever, we have a pixel, we have a resolution, or voxel in 3 dimensions, where the number of points, data points we have, times delta x would be Lx. This is, in a sense, the smallest distance that we can understand and see features. And that's that delta x that we're beginning to talk about now in this problem, and we'll return to in more detail in chapter 13.